Okay. Thank you very much for that kind introduction. Indeed, I remember visiting the Institute of Physics a few years ago. I'm sorry not to be able to come in person this year, but hopefully soon in the future. So thank you also for the invitation to talk about looking beyond the standard model with the standard model effective field theory. And on this first slide, I taken a quotation from the Chinese strategist Sun Tzu. The direct method may be used, but indirect methods will be needed in order to secure victory. The direct and the indirect lead on to each other in turn. It's like moving in a circle. I don't know whether we're thinking of circular colliders. Who can exhaust the possibilities of their combination? So I think this summarizes my attitude towards the standard model effective field theory. Of course, it's great to look for new particles directly, but often indirect methods telling us about the possible existence of new particles can also be useful. And that's what we're going to be discussing today. Okay, so I don't need to remind you about the standard model, and I don't think I need to remind you either that until the discovery of the Higgs boson in 2011, only the top two lines of the famous standard model Lagrangian had been tested. And now, of course, we're trying to test the second set of two lines, which includes the Yukawa interactions, the Higgs kinetic term and the Higgs potential. And this is very much at the top of the order of business of the LHC. So what do we have so far? So this is a summary of measurements by the CMS collaboration at the LHC. Many measurements of the production of intermediate vector bosons, photons, jets, the top quark, and of course the Higgs boson. And I think it's striking how within a decade we have made so many measurements of the Higgs boson and learned so much about its properties. So far, all these measurements at the LHC are consistent with the standard model. And I will come back later to what the standard model effective field theory tells us about the current status of that consistency, of that agreement. So the discovery of the Higgs boson was a tremendous milestone in particle physics. Of course, when it was initially discovered, we couldn't be sure that the particle that had been discovered was indeed the Higgs boson. I mean, the experiments discovered it using the procedures that they developed to look for a Higgs boson. But wasn't this indeed the missing piece in the particle jigsaw puzzle? If you continue with the jigsaw puzzle analogy, is it the right shape? Is it the right size? It's a little bit like when you are looking for a missing piece of the puzzle, and you find a piece of cardboard in the back of the sofa, the picture's been rubbed off. Is this the right piece to complete the jigsaw? So I think it's fair to say that the particle that has been discovered certainly walks and quacks like the standard model Higgs boson. One of the key tests, of course, is whether it couples to other particles proportional to their mass with a scale given by the vacuum expectation value V of 247 GeV. And there's been various tests of this. This is a plot, again, from the CMS collaboration, showing that the couplings to the top quark, the W, the Z, the bottom, the tau, and the mu are all consistent with being proportional to those particles' masses, exactly as predicted by the Higgs structure of the Standard Model. So I think that Peter Higgs is entitled to smile. So you might say, well, okay, the Standard Model is complete. What else is there to do? And here I'd like to take a quotation from a poet, T.S. Eliot, who wrote that to make an end is to make a beginning. The end is where we start from. And that's very much my attitude towards the current status of particle physics. Yes, we have found the last particle that was predicted by the Standard Model. That provides us with a basis for looking at possible physics beyond the Standard Model. And a good starting point is to review the Higgs boson, in particular because everything about the Higgs is puzzling. So here I've written out at the top there the pieces of the Standard Model that involve the Higgs. So the first term is the Yukawa couplings of the Higgs to fundamental fermions. And here immediately we encounter the so-called flavor problem, or perhaps I should say flavor problems. We have a very bizarre pattern of fermion masses. We have mixings that we don't understand. We measure them, but we don't understand them. And of course, now with data in particular from LHCb, there are hints that there may be deviations from the Standard Model in the flavor sector. So you've already heard a little bit about those deviations from Luca Silvestrini. You're going to be hearing more about them from Gino Isidori, and I'll say a little bit about them in my final lecture. Then the second term is the Higgs mass term, mu. So this poses problems of naturalness. Why is this parameter so much smaller than the Planck scale, which is the fundamental scale associated with gravity? And what stabilizes this fantastic hierarchy between the gravitational and the electroweak scale? Then we come to the Higgs quartic coupling, lambda. So the puzzle here is that if we use the renormalization group to run the parameters of the Standard Model up to high energies, we discover that the Higgs self-coupling turns negative at some scale way before the Planck scale. And this then raises the possibility that empty space, the electroweak vacuum, is unstable. Now, I should say that the lifetime for this instability is much longer than the age of the universe so far, but this still poses, to me, a fundamental philosophical problem. Then we've got the cosmological constant term, V0. So you might say, well, that doesn't involve the Higgs boson. But I would say implicitly it does, because when we write down the Higgs potential, we are making contributions to the cosmological constant, to the dark energy, if you prefer, which are many, many orders of magnitude larger than the measured value of the cosmological constant or dark energy. So this is also, this magnitude is also intrinsically linked to the properties of the Higgs boson. Then we have a second box at the top there, namely the possibility that there may be higher dimensional interactions involving the Higgs boson and, of course, other particles of the Standard Model, which would appear in general in extensions of the Standard Model to include new heavy particles. And that's going to be the primary focus of what I'm going to be talking about today. I won't just be talking about high dimensional terms involving the Higgs boson, but they will certainly play an important role. So you've heard a lot about effective field theories in these lectures, and I am not going to go through technical details. But I did just want to remind you that effective field theories actually have a long and glorious history in particle physics. So if you think back to the 1930s, the theory of electrodynamics, quantum electrodynamics, had already been written down, in particular by Dirac. And that had interactions between the photon and the electron, for example. And those interactions had dimension 4. You can regard those QED interactions as somehow being the standard model of the 1930s. But in addition, we knew that there were weak interactions. And Fermi wrote down a 4-fermion theory of the weak force, which was in some sense the first effective quantum field theory. Now, when you couple together 4 fermions, you get an effective dimension 6 operator. And for more than 20 years, there was discussion going on about what was the form of that dimension 6 fermion interaction. Was it scalar? Was it pseudoscalar, vector, axial, maybe tensor? And I think there was a general feeling that this interaction was not fundamental and that it was due to the exchanges of massive particles. Now, of course, as soon as you fix the Lorentz form of that dimension 6 interaction, then that gives you a clue as to what sort of massive particles there may be. So indeed, V-A theory was proposed, a current interaction, that told you that the intermediate particles should be massive vector bosons. And that, of course, led on to spontaneously broken gauge theory, such as the Standard Model. In parallel, in the 1930s, Yukawa had written down a Meson theory of the strong nuclear force, which he thought would be exchanged due to the exchanges of mesons, for example, the pion. The pion, of course, has a larger mass than the typical nuclear scale, although it's small on the particle physics scale. Then in the 1960s, people studied the dynamics of pions, and they discovered that they had derivative interactions, which are characteristic of chiral dynamics. And that was a very important clue for the formulation of QCD. In particular, the idea was popular that there should be gluons mediating interactions between quarks. But this chiral symmetry told us that those gluons had to be vector gluons, and so laid the basis for QCD. So effective field theories played key roles in establishing both the electroweak and the strong sectors of the Standard Model. So the Standard Model effective field theory is a powerful way to analyze the data which is emerging from the LHC. So what does it do? It assumes that the Standard Model Lagrangian is correct as far as it goes, in particular the quantum numbers of the particles are correct, but that the theory is incomplete and is supplemented by additional interactions between Standard Model particles due to the exchanges of heavier, as yet unseen particles. Now, one of the beauties of the Standard Model effective field theory is that it enables us to do a common global analysis of Higgs data together with other data sets. And you already heard about some examples of that, in particular from Eleni a couple of days ago. She was talking about the analysis of the top data set, which, as we will see later, is a very important ingredient in making a global analysis. So in my view, the Standard Model effective field theory is the most efficient, the most effective way of extracting the largest amount of information from LHC and other experiments. And it provides a model-independent way to look for physics beyond the Standard Model. So a lot of what I'm going to be saying in the next part of the lecture is based on a paper that I wrote a bit over a year ago with Maeva Madigan, Ken Mimasu, Veronica Sands, and Tivon Yu, in which we did this global analysis of data, including dimension 6 operators. Of course, in the SMEFT, you should consider eventually operators of dimensions higher than 6, and I'll come back to that towards the end of my talk. But let's, for the moment, focus on dimension 6 operators. So their coefficients are typically scaled by some high new physics scale, lambda squared, with a dimensionless coefficient. Now, there's an awful lot of these operators, as you've heard. And so for that reason, it's common to simplify the analysis by assuming some sort of global flavor symmetry, either assuming that dimension 6 operators are flavor invariant, so that would be postulating a global SU3 to the 5th flavor symmetry, or maybe breaking it for the top quark or for the 3rd generation. And what I'm going to be talking about, I'm going to be doing 2 analyses, one assuming SU3 to the 5th, and one assuming SU2 cross SU3, SU2 squared cross SU3 cubed. Now, another simplification which I'm going to be making is working to linear order in the operator coefficients, i.e. order of 1 over lambda squared. This means including interference between SMEFT contributions to amplitudes and standard model amplitudes, but not including terms where the SMEFT operator combines with itself. And as you heard, this is, of course, an approximation which can be doubted in some cases, but I won't be discussing that in great detail. Okay, so here I've got a table of the dimension 6 operators in a little bit more detail. So there's operators which just include bosons, there's operators which involve pairs of fermions, 4 fermions. And in this table, there's color coding according to the various different data sectors, which I'll explain in a bit more detail in a moment. Notice also the gray shading, the gray cells may violate SU3 to the 5th symmetry. Now, I've highlighted some of the dimension 6 operators that I will not be talking about in this lecture. So outlined in green are operators that contribute to flavor anomalies. Outlined in purple are operators that contribute to baryon decay. And perhaps I should also mention some operators in the middle there, which can contribute to anomalous magnetic and electric dipole moments. So those are operators that I will not be discussing in this lecture, but I will be returning to them at the end. So the color coding on the previous slide corresponded to electroweak precision observables, highlighted here in pale blue. Other bosonic operators, highlighted in beige, and Yukawa type couplings, highlighted in green. Now, if you assume flavor universality for the dimension 6 operators, then there's a total of 20 dimension 6 operators which you should include in your global fit. On the other hand, if you assume that the flavor symmetry is broken in the top sector, then the global flavor symmetry is broken down to SU2 squared times SU3 cubed, and you get a total of 34 operators. So these are the 2 frameworks that I'm going to be discussing in the course of this talk. So here I've illustrated the fact that many of these operators contribute to many different data sectors. So I've separated out top sector data, diboson production data, electroweak precision observables, which are highlighted here in purple, TT bar production data in green, and Higgs data, which are highlighted in red. So the fact that all these boxes overlap indicates that it's important to include all the data sets when you're doing a global analysis. So for example, these operators here, these operator coefficients listed here, contribute to and are constrained by electroweak precision data, as well as Higgs data, top data, for example. So what we did in our paper, in our global analysis, was, as I said, to look for possible evidence of physics beyond the standard model. In fact, what we finished up with was constraints on physics beyond the standard model, some constraints that appear at tree level, but I also mentioned specific analysis, which we did at the loop level. Now, one feature of this global analysis that I want to emphasize is that since dimension 6 operator contributions typically grow with energy or with transverse momentum, measurements at, for example, high PT or large invariant mass intrinsically tend to have higher sensitivity to dimension 6 operator coefficients. And that's shown here in this compilation taken from Atlas. If you look, for example, at Higgs production data at higher PT, you get greater sensitivity to the dimension 6 operators. On the other hand, of course, there's fewer Higgs bosons produced at higher PT. So you gain a little bit, but you also lose on statistics. Anyway, what the experiments are now doing, and what we did in our global analysis, was to use the binning of data, for example, on the Higgs, but also other data in bins, for example, of transverse momentum, using the so-called STXS prescription. So here I've superposed some tables taken from our paper, where we listed all the 328 measurements that we include in our global analysis. So, for example, there's precision electroweak data, there's diboson production, there's information on the transverse momentum of dibosons, there's, of course, Higgs data, there's STXS information on Higgs production, there's top data. In addition to LHC, we also included Tevatron data, and of course, the electroweak precision data are dominated by previous lab data. So let me jump straight to showing some results. So this is from our flavor universal analysis, assuming that dimension 6 operator coefficients have an SU3 to the 5th symmetry. So here we have the constraints on the individual operator coefficients CI, normalized for the case where the new physics scale would be 1 TeV. What you can see is that all the operator coefficients are consistent with being 0. So there's no evidence for physics beyond the standard model. I should mention that the top two plots here are for an analysis in which we switched on the operators one at a time. The lower pair of plots are where we include all the operators simultaneously, and results for each individual operator are obtained by marginalizing over all the other operator coefficients. So when you do that, when you include all the operators simultaneously, the constraints become weaker. And that you can see just by looking at the vertical scales in this third box here and comparing them with the first box, which is where we only switched on one operator at a time. Now the histograms here show you the constraints that you get if you assume that the operator coefficients Ci are 1, and these then give you constraints on the new physics scale. And you can see that in this case, you get constraints which are typically at the TeV scale, maybe even 10 TeV in some cases. Those are the filled histograms, and the unfilled histograms are for other assumptions about the coefficient Ci, which I won't go into in detail. Okay, so the bottom line from this slide is that there is no significant evidence for physics beyond the standard model, and you're getting constraints on the new physics that may be at the level of 10 TeV, somewhat less in other cases. So we also analyzed which measurements constrain which operator coefficients. And you can see that in some cases, there are measurements that are powerful for containing many different operator coefficients. And you can also see that there are some cases where some operator coefficients are constrained strongly by several different measurements. So this again emphasizes the point that it's important to do a truly global analysis. So the previous case was assuming flavor universality. As I already mentioned, we also did an analysis which was we call top specific, where we allowed the operator coefficients involving the top quark to deviate from flavor universality. So then, as I already mentioned, we get a whole bunch of additional operators, total of 34. In this case, the constraints are sometimes somewhat weaker. That's in particular the case in the top sector. So Eleni discussed that a couple of days ago, and I'll be coming back to that in a moment. As previously, the top two plots here are where we switch on one operator at a time, and the lower two panels are when we switch on all the 34 operators, and then we marginalize over all the other operators to get the coefficients, limits on the constraints of any particular operator coefficient. Again, we don't see any, to my mind, significant evidence for physics beyond the standard model, although you may notice that there are some cases where the coefficients of the operators are deviating a little bit from zero. I would say not significantly, and I'll come back to that in a moment. So clearly, the operator coefficients are correlated, and we did a detailed correlation analysis. So what you find is that there are quite strong correlations between the different operators that appear in electroweak position observables and the bosonic sector, like diboson production. There are also strong correlations within the subsector corresponding to top observables. The correlations between if you like, the bosonic operators and the top operators are weaker, but they cannot be neglected. If you look in detail, you find that there's many instances where there are significant correlations between top operators and, for example, electroweak operators. So here is one example where you see the interplay between the various different data sets. So the beige shaded areas here correspond to the Higgs data. If we include TT bar Higgs production, then we get this green ellipse. If we include other top data, we get a purple ellipse. And finally, if we do a full global analysis, we get a blue ellipse. So I think this, I should have perhaps explained, this is a so-called triangle plot where we focus on the operator coefficients of a few operators that are particularly important for top data. I won't go through the detailed definitions of them. So these are plotted along the vertical axis, and also you see operators plotted along the horizontal axis. Now, if you look very carefully at this, you'll find that there's maybe a little hint of some deviation. So the standard model would predict that black dot there, and that lies outside the ellipse given by the global analysis. In particular, it looks like the data want CG coefficient of a multi-gluon operator to be non-zero. So where does that come from? So this plot, I think, shows the biggest discrepancy that we found with the standard model. And it's in the TT bar invariant mass distribution. So the data are shown as the black points here. And our best fit is shown by these yellow stars. And it's not such a great fit to the data. And in particular, there seems to be some problem close to the TT bar threshold. Now that best fit has a non-zero coefficient for this multi-gluon operator. However, there have been analyses of the contributions of this operator to multi-jet production at the LHC, something we didn't include in our analysis. And those data favor a small value of CG. So first of all, I don't think this discrepancy that we found is particularly significant. And secondly, I think it's probably ruled out by these other data. So something else that we did was we basically diagonalized the correlation matrix that I showed you earlier on to find out which combinations of operators were constrained strongest and which weakest. So that's shown here. So some of the operator combinations are constrained beyond the 10 TeV level, where some operators are constrained only at the maybe a couple of hundred GeV level. And if you look carefully at these, you will find that the strongest constrained operators are those which are dominated by electroweak and Higgs data, whereas the weakest constrained operators are those that contribute primarily to the top sector. So this, I think, emphasizes that more precise measurements of the top quark production at the LHC is one of the going to be one of the most interesting future horizons in LHC physics, as well as measuring the properties of the Higgs. Okay, so now I want to discuss the implications of this analysis for specific single field extensions of the standard model. So here I've listed all the possible single field extensions of the standard model, which have various different spins, bosonic, fermionic. In particular, if we look at the bosonic extensions, we have some of spin 0 and some spin 1. And those are the ones that I'm going to focus on in a moment. So each individual extension of the standard model can contribute to a limited number of the dimension 6 operators. So here, again, I've highlighted in red the spin 0 operators, and you see some of them contribute to very few dimension 6 operator coefficients. In purple, we have vector operators, vector extensions of the standard model. In that case, typically they would contribute to more operator coefficients. So we did an analysis of the mass constraints that you get on the scalar and the vector extensions of the standard model from our global analysis. So the mass limits are assuming that the coupling to standard model particles is 1. And we also list the limits on the couplings if the mass is 1 TeV. And from here, I think one of the take-homes is that simple scalar extensions of the standard model would require the scalars to weigh more than a TeV or so. And in the case of possible vector boson extensions of the standard model, then the constraints would be even stronger. However, I emphasize again that these constraints on the masses of scalars or vectors beyond the standard model, the precise mass values depend on the assumed coupling to the standard model particles. And so there is some scope for varying the coupling and thereby possibly weakening the mass constraint. Now, I mentioned that we also looked at constraints arising at the loop level. And a good example of this is provided by supersymmetry. And these are a couple of plots showing the constraints that we get on possible light stop squawks. Now, these would contribute to these operator coefficients at the one loop level. So you see the characteristic factors of 4 pi. So you might say, well, no, the constraints are going to be relatively weak. Well, that's true, but nevertheless, I think they're interesting. The constraints depend on the mass of the stop squawk, but also on the mixing. I'll remind you that in supersymmetry, there are actually 2 stop squawks which can mix, and depending on the way in which they mix, the strength of the constraint varies, but it's typically a few hundred GeV. So it's interesting to compare this indirect constraint on stop squawks with the direct constraints that you get from searches for stop squawks at the LHC. So you see in this plot taken from the Atlas collaboration that there are many different searches which contribute to excluding light stops. There's quite a patchwork of these various different constraints. Now, the indirect constraint is in some sense much simpler because it only depends on the mass of the stop squawk and the mixing. So there's many fewer parameters that enter and the constraint which you obtain is, I said, put here almost model independently. Certainly it's less model dependent. Okay, so I talked earlier on about the constraints that you get from the data switching on one operator at a time. And I talked about the constraints that you get if you switch on all the operators. But I also said that if you look at a typical extension of the standard model, then it generates some operators, but not all of them, but a limited number typically. So what we did was we did a general analysis where we looked at all possible combinations of 2, 3, 4, and 5 SMEFT operators. And then we switched on these combinations and looked to see whether they gave you a better fit than the standard model, to see whether they pulled the best fit away from the standard model value. So here in beige, this is what you get if you look at combinations of 2, 3, 4, 5 operators that don't involve the top quark. In blue, if you include the top quark, sorry, only top quark operators. And green, arbitrary combinations. So what you see from this is that, well, the topless sector fits the standard model very well. The top sector doesn't fit so well, but I think that none of these pulls is really excessive. And we looked at some of the combinations which give you the maximum pull to see whether there was any hint there of some particular extension of the standard model. But I would say that this analysis doesn't give you any significant hint of beyond the standard model physics. Now, I remind you that in our analysis, we made flavor universality assumptions. Now, we did relax flavor universality in the quark sector. In our analysis, we did not relax flavor universality in the lepton sector. And of course, that's where there are hints of possible new physics coming from B decays that you heard about already from Luca Silvestrini. You'll be hearing about them some more from Gino Isidori, and I'll say a little bit about them on the final day. Now, but just for reference, the sort of typical pulls that you would find from the operators that would contribute to these B flavor violating decays, the typical pulls are 10, 15, 20, 25. They're way, way, way bigger than these relatively small deviations from the standard model that we found here in this flavor universal analysis. Now, I should compare with an analysis that came out a few months after ours, which included the contributions of dimension 6 operators at order 1 over lambda to the 4th. Now, this analysis made at least one simplifying assumption, namely they assumed that the precision electroweak data agree exactly with the standard model, which of course is going beyond what the data is telling us. So qualitatively, the results are not so different from ours, although they find tighter constraints in general. Also, they didn't do such a broad analysis of possible scenarios of physics beyond the standard model, just because when you go to a quadratic analysis, then the computing time is a lot longer. Now, one issue when you go to quadratic order in dimension 6 operator coefficients is, what about dimension 8 operators? Because dimension 8 operators, their interference with the standard model would contribute at order 1 over lambda to the 4th also. So I think if one wants to do a complete analysis of order 1 over lambda to the 4th, one has to worry about dimension 8 operators as well as dimension 6. But that's something which has not been done in any detail so far. So what can we say about dimension 6 operators? This is how dimension 8 operators. But I just want to mention a few windows of opportunity where one can identify effects which do not receive contributions from dimension 6. The first contributions come from dimension 8. And these include light-by-light scattering, gluon-gluon collisions to produce gamma-gamma or Z-gamma, and neutral triple gauge couplings. So the first measurement of light-by-light scattering was done at the LHC by the ATLAS collaboration, who looked at peripheral heavy ion collisions. Now, why is light-by-light scattering interesting? Well, it appears in the standard model through loop corrections. And this was first calculated by Heisenberg and Euler back in the 1930s. So this is one reason why one might be interested in light-by-light scattering, loop effects in the standard model and beyond. But there's also another idea that was proposed in the 1930s by Born and Infeld, which was the idea that quantum electrodynamics might be nonlinear. And they suggested a specific modification of the QED Lagrangian based on what they called the Unitarian idea that there should be a maximum electromagnetic field in the same way that there's a maximum velocity, i.e. the velocity of light. So that was back in the 1930s. In the 1980s, this nonlinear modification of electrodynamics was actually derived from string theory. And it was shown, in particular by Bachas, that this modification was actually related to a maximum velocity for branes, extended structures that appear in string theory. So the work of Bachas, basically 60 years later, confirmed the intuition of Born and Infeld. So we used the ATLAS data to constrain the possible scale of Born and Infeld, which corresponds to the separation between the branes in string theory. And we got numbers of the order of a couple of hundred GeV. So that was one possible window on dimension 8. Another possibility is to look at gamma-gamma production at the LHC, which can be used to constrain dimension 8 operators coupling gluons to photons. So here again, there was some ATLAS data from a few years ago. There's 8 dimension 8 operators that can contribute. And one particular combination of these would appear if you had a Born-Infeld type extension of the standard model. So we derived various constraints on the coefficients of these dimension 8 operators, and we got constraints of the order of a TeV also, with prospects for much stronger constraints with possible future colliders. So recently, also with my previous collaborator, Xiaofeng Ge, and with Kai Ma, we looked at the constraints that you get from glue goes to Z gamma. And this also gives you constraints on dimension 8 operator coefficients at the level of a TeV also. And this is actually a compilation from our paper showing how the LHC and future colliders already do, or in the future possibly could, constrain the coefficients of dimension 8 operators. And we also included a dedicated analysis of the Born-Infeld model, where you get a particular combination of dimension 8 operators. Another possible window for dimension 8 operators is provided by neutral triple gauge couplings. So these don't get any contributions from dimension 4, not in the standard model, or from dimension 6. The first contributions appear at dimension 8, and we looked at how you could probe these dimension 8 operators using the process E plus E minus goes to Z gamma, and I'm currently involved in an extension of this analysis to include the LHC. So again, the prospective constraints on operator coefficients are prospectively in the TeV range. Okay, so that brings me to the end of what I wanted to say. So remember Sun Tzu. Search for new physics indirectly as well as directly. SMEFT, as I hope I've convinced you, is an effective model-independent tool for probing indirectly possible physics beyond the standard model. And you can use it to analyze jointly precision electroweak, diboson, and top quark data from the LHC, as well as Higgs data. So our current analysis indicates that the scale of new physics is probably bigger than a TeV, but that depends on the precise BSM scenario you have in mind. So far, there is no clear evidence for any particular beyond the standard model scenario. And discussed a little bit at the end, but I didn't really develop the point that the standard model effective field theory is very useful for assessing the sensitivities of proposed future accelerators. So I leave you with this picture here. So here's a standard model. It's doing fine, but maybe below the surface, below the visible part of the iceberg provided by the dimension 4 terms in the standard model, maybe there's an enormous submerged part of the iceberg consisting of SMEFT operators with dimensions bigger than 4, and maybe they will soon sink the Titanic, which is the standard model. Thank you.
Thank you so much, Professor Ellis. Questions? Monimala, please.
Thank you, Professor Ellis, for the very nice and detailed technical discussions. I have a very naive question. So among the different data sets that you were showing, so which one is the most constraining? I mean, can you pinpoint that some of the data set is more constraining, or?
Okay. Well, the precision electroweak data are the most precise constraints, but for a limited set of operators. Then I think the next strongest constraints are those coming from Higgs production. Also helped a little bit by production of vector boson pairs at the LHC and at LEP. And the least constraining are the top operators. Are the top measurements so far. Of course, you know, that will improve in the future. But the point I would like to mention is that these are all coupled together. If you want to get the best possible constraints, you have to do this sort of global analysis. And if we look to the future, I think that so the LHC will also contribute to precision electroweak measurements. But if we're thinking of a possible future circular E plus E minus collider, like CEPC in China or FCC-EE at CERN, they will provide tremendous improvements in the precision of electroweak measurements. So that's something to watch out for, as well, of course, as greater precision in Higgs measurements.
Okay, thank you.
Okay.
Anybody else? Okay, I don't see any more hands. Ognivo, please, yes. Ognivo?
Hello.
Hello.
Yeah, we can hear you. Yeah.
So my question is that so that single field extension, and if I do that and then put the electroweak and other precision data, then the limit is quite stringent. But now if I add like many particles, I can actually relax those limits a little bit, right?
Yeah, in general, that's correct. So it's a sort of impossible combinatorial problem to analyze all possible combinations of heavy fields beyond the standard model. So we analyzed, as we saw, the single field extensions. And then we analyzed arbitrary, simple multi-operator extensions. But I think the field is very much open to anybody who has some scenario with perhaps more than one particle beyond the standard model to see what sort of constraints you obtain in that model from this global analysis.
So like I can do the exercise, let's say, to add another doublet and do the same extension and can relax these bounds, right?
Yeah, so maybe if I just quickly go back.
Yes.
Yeah. So here's a sort of dictionary. So you could, in principle, combine whichever subset of these single field extensions you like to make a multi-field extension. And then these operator coefficients here, and you get contributions from several different operators. So does that answer your question?
Yes, yes. Okay.
Okay.
Anybody else? Okay.
I see the
Shubhendu, yes. Yeah.
Yes. Hello, Professor Ellis. I was thinking that if you find some blind directions in this operator space, I mean, does it tell you anything about the UV theory?
So thank you for that question. So if you look here, you'll see that there are no completely blind directions. On the other hand, there are some directions which I might describe as short-sighted or myopic, okay? So for example, this is one particular direction where the constraint is around 100 GeV. And if we look in detail at that, that's one which the most important constraints comes from single top production. So in that particular case, that's telling you that you could bring the scale of new physics down very low. And so that might be an interesting example to think about how you would look directly for the new physics that might contribute to that operator. Maybe that new physics is within reach.
Okay, yeah, okay, thank you.
And then, of course, if you go off to the left here, then you can get some other examples of combinations of operators which are maybe not as short-sighted as this one, but also only see as far as 200 or 300 GeV.
Okay, yeah, thank you. Yeah.
Anybody else? Okay, while we can think of other questions, maybe I will ask a question. Professor Ellis, I was wondering that, of course, we have a set of measurements from LHC. So now that run 3 will give us data at slightly higher energy, which we can do only total cross-section measurements, not differential cross-sections. So will it really help in this EFT analysis, such data, after 3-4 years?
Yeah, so run 3.
How will it constrain? Yeah.
So as you said, run 3 is planned to be at a slightly higher energy, which will have some advantages if you're looking, for example, at the tails of kinematic distributions. So I talked about the greater sensitivity of high PT Higgs production to dimension 6 operators. If we're talking dimension 8 operators, a higher center of mass energy also benefits you, of course. So there'll be some benefit from the small increase in the center of mass energy. But of course, there will also be benefit from the fact that the total luminosity will double. Run 3, I think, will give us a significant step forward. Of course, the big leap forward will come with high luminosity LHC in a few years' time.
So right now, these EFT analysis do not want to consider the limits from the double Higgs measurements because they are only limits. Is that true?
So the double Higgs limits at the moment are not very constraining.
Yeah, exactly.
Now, actually, together with Ken Mumasu and a student, we're looking at the interplay between the current Higgs measurements and double Higgs production. So at the moment, double Higgs doesn't provide any additional information. The question would be, well, at high luminosity LHC or FCC HH, how does the information you get there from double Higgs production compare within the SMEFT, within that information that we already have from Higgs, or that we will potentially get from single Higgs production in the future? And so this we're analyzing in particular single field extensions of the standard model. But in general, that's a very model dependent question.
Okay. So maybe for run 3, one should do many more top related differential measurements, because as you said, they are the least constrained at the moment and the top cross section is high. So maybe one can add to the basket.
I think it's a coupled theory experimental issue. So on the one hand, of course, we would like more precise experimental measurements, including actually close to the TT bar threshold, where, as you saw earlier on, there is yes, there we go. So here, the measurement is quite a bit higher than the standard model. And generally, the trend in the data is a function of the TT bar mass, may be a possible indication of tension with the standard model. So clearly, we'd like better measurements of that. I think we would also like to be sure that we have control over the perturbative QCD contributions to the standard model cross-section. So there's work for theorists as well as experimentalists.
Yeah, okay. And similarly, maybe diboson measurements will be more useful than just measuring triboson production cross-section. Because again, it will be not very precise.
I don't know that I go so far as to say that they're more interesting. I think both of them are interesting.
Yes, sure.
But I think that what is going to be interesting is diboson measurements at large invariant masses or at large PT, which, as I've tried to emphasize, will be most sensitive to SMEFT operators.
Okay. I don't see any more hands raised. So let's thank Professor ELLIS for the very nice, interesting and illuminating talk. And of course, we will follow it up with
Okay.
more analysis. So thank you very much once more. And have
Okay.
a
So thanks
good day.
again for the invitation, and I'll be seeing you again on Saturday.
Yeah, thank you.
Yes,
Bye.
so thank you, Professor ELLIS, and we will again resume at 5:30 with our next talk. Okay, thank you. Thank you.